All right. Welcome to my presentation on GPU computing made easy through G²CPU. Before we jump in, I need to turn on my clicker. There we are. So who am I? I'm Nathan. I'm a CLA, also freshly minted LabVIEW champion. Started using LabVIEW about 10 years ago, so still quite new at this, I dare to say. You might know me from some previous presentations, so I did some fun things with FPGA accelerated computing, and also did some presentations on running LabVIEW natively on Android and iOS. This is also a shameless plug. Should you be interested in that, let me know. I'm definitely up for some more of these presentations. And currently I'm employed at QPLOX Engineering in Leuven, where I'm working as an R&D architect. I used to be deployed at ASML. Currently I'm deployed at IMAC. Before that, I used to work for National Instruments as an application engineer, so you might recognize me from there. And also have a fun story. The last time I was at Glasgow, I presented LabVIEW Core. So quite simple, teaching data types and arrays. Now I went the long way around to, well, pretty much do the same thing all over again. Okay, so within this presentation, I want to touch a couple of different things as an introduction to why and how G²CPU is what it is. Also going to talk about the benchmarks, because you can't talk about a high-performance computing toolkit without talking numbers and what it actually means. Also different editions that are going to be available, and maybe even longer term roadmap, and then afterwards we can have some questions. So let's start with what is LabVIEW. I started to think, okay, what is it? What if we strip away the buzzwords, the marketing, the NI hardware, the small lab programs that we can find wherever we are deployed? What stays left? What makes LabVIEW great compared to C++ or Python? Well, of course, it's subjective. To me, it's a benchmark for low-volume applications, applications where only 5, maybe 10 exists in the whole world. It's high speed. You have low-level access. So loops processing data at 80 megasamples per second is not a big deal. It's also cross-platform, so you can actually reuse your code. And yeah, we tend to use it for industrial applications. It needs to be reliable, it needs to be stable. We need to be able to debug it and immediately know what's going on, no doing a dozen printfs. Now, this is all well and good, but why is that? So for me, it's compiled. You directly know if your code is running or not. There isn't, let's compile and let's wait until the end of the day to compile and then go through 100 debug messages and then spend another 2 days figuring it out. We have debugging tools, probes that we can just place, and they change their behavior depending on the data type, not trying to serialize it to a string and trying to interpret it. No, we can do with it what we want. We can visualize, there are probes with graphs, we can make our own probes, we can do a ton of different stuff. There's execution highlighting. There's a flow in LabVIEW. There are ways to break that, but people that are starting to use it, it's best that they can keep on using that. And of course, each function has a UI. So most functions, we can actually test them on their own. So if something's not working, we can just pluck the function out and test it on itself rather than trying to test it in its larger environment. Or, well, unit tests are important, but when you're starting quickly testing something, just run, test, okay, good, and then afterwards you can run a unit test. Also, code reuse, extreme code reuse, I dare to say. You can make a single VI, and it can run across multiple types of CPUs, operating systems. The same VI that you ran on x64 system, you can suddenly run on a real-time target that is running an ARM CPU. If your code is well written, your algorithm is well written, you can pluck it up and suddenly place it on an FPGA, and also regardless of the bitness, you can have different environments working, which is great. You can, your algorithms, you only have one algorithm to maintain. You just put it on GitHub, and it's only one thing to maintain rather than having 20 variations of it, each one with their own little quirk. Maybe one has a bug fix, but the other one hasn't, and it can become a mess. So for me, code it once and code it right. It's quite an important motto, so I prefer to go the extra mile and then make sure that my code works everywhere. Just you gain some instability. How did I translate this to G²CPU? Well, first of all, I started to look around. Actually, neither arose where I need GPU computing myself and started looking around what is already available. And I had a lot of problems. First of all, the current commercial libraries are, in my opinion, a bit limited. First of all, platform limited. Most of them focus on CUDA, so but those technologies aren't always available. So you might have a gaming laptop which has a CUDA GPU in it, or an NVIDIA GPU in it, but it also has a CPU in it, and that CPU might have an internal GPU. But what about our PXIs? They just have an internal GPU. They don't have a CUDA card in them or an NVIDIA card in them. There are boards available, but it's not always possible to load those in. Maybe you have some industrial computer with strict power requirements. Maybe it needs to be in a clean room where you can't just put a graphics card with a fan in it. All that becomes quite important. So it's already a little bit foreboding, but let's decide at runtime. Let's make our algorithm such that it's implemented, and we can decide later on where it needs to run. Maybe even dynamically let the program choose what's the best. Another thing is feature limited. The ones I tested, they too closely resemble LabVIEW. So when we're programming with LabVIEW, we're used to LabVIEW being the fastest thing. If we do a for loop, it can run at the maximum speed of the system itself. Well, that's no longer the case when we're talking to the GPU. There's so much overhead, it doesn't work. So it would be great if more complex things, instead of having for loops, let's pull that to the GPU and have discrete functions available for that and just decide, okay, I want to work in this dimension, or we need to do it this way or that way. Let's push it all to the GPU. And also, yeah, if certain functions aren't available, yeah, suddenly you need to develop it yourself. DLLs, it takes a lot of time, and also just getting the knowledge. It's a pain. So eventually I landed on, with my solution, I landed here. So first, LabVIEW is not an island. Let's look around what others have done rather than constantly try and reinvent a wheel. So let's not start from scratch. Others have had the same problems. They've had the same problems for years, 10, 15 years ago. So why not look at them and then see if we can join them? So again, shameless plug to my presentation. So running LabVIEW on Android and iOS, it was built based on Cordova. If we're doing version control, we don't have custom systems mostly. We use Git or SVN. Even ASCII-doc is the basis for anti-doc, so why reinvent the wheel? Or in this case, after a lot of searching, I landed on Arrayfire as the basis for high-performance computing. Okay. So Arrayfire is a set of DLLs. It's a platform, it's a set of DLLs that's been actively developed upon for 10 years, actually longer. So they've already gone through the pitfalls that if we start using GPU computing, we're bound to fall in. So they already had the issues, they figured it out. Let's join them rather than to catch up. Also, it's open source, which is great. If we need to make variations specific for LabVIEW, we have the possibility to do so. They support CUDA, OPENCL, x86, ARM, and those can all be chosen during runtime, saying, hey, I want this code now to run on the CPU. I want to run this on an NVIDIA graphics card. I want to run this on the iGPU. You can choose dynamically, even to the point where while one GPU is doing some calculations, you can quickly switch over to the CPU to do some calculations, and then switch over to another GPU while the other are working. And also, interesting for us, there is support for Windows and Linux. So it's pretty much exactly what I was searching for, so I started with that as my basis. Another interesting thing is they already have a ton of compatibility with other languages, C, C++, C#, Python, for people that are working with data scientists, MATLAB when we're communicating with scientists, Ruby if you're working with servers with Ruby on Rails. All those languages already have plugins for this framework. So yeah, we can use that to our advantage. If someone's working with Python, we can just give them an Arrayfire handle and they can continue working with that rather than doing the entire song and dance that we're used to, where we need to get some kind of standard going, which is often quite custom, and it's a pain. So with this, it will become, or it is quite easy. So now let's have a look at what I try to add to Arrayfire with G²CPU. Arrayfire does have the tendency to crash if you don't treat it nicely. Data pointers that are not initialized, that kind of stuff. So I try to make it feel like home, make it feel like LabVIEW. So in this case, visual feedback, data types, dimension count, so the wires change depending on the size. Syntax validation. If you're not allowed to do something, you immediately see it is allowed or it isn't, instead of waiting for Arrayfire to crash, which would crash your entire application, except if you're running multiple executions. Quick little thing. So adding two different arrays of different sizes. In LabVIEW, we're not used to being able to do that. Arrayfire does have certain abilities to do that, and I'm working on solutions to also bring that to LabVIEW. Just quickly sidetrack here. Another thing I'm trying to add, or have added actually, is probes, but not in the way that we're used to. Normally when we probe an array, we just see scalar values on the screen. It can be a pain to go through. What I try to do here is give a bit more. If you have a 2D array, let's visualize it in a graph. Let's make it visible. We're talking about big data here, so better to see the bigger picture. Also, you will see, okay, where is this array? Are we talking CPU? Are we talking the GPU, iGPU, OPENCL, CUDA? All that is directly visible. Lastly, like I said, how am I going to make it feel like home? There are a ton of functions in Arrayfire, but they're not LabVIEW-esque. So what I try to do is, get some of those functions in there that we're used to if we just need to quickly do something. So most of the array functions I made an analogy for in G²CPU. So if you just quickly need something, you don't have to go through the entire gambit of Arrayfire. You can just use these. Also, utilities. I'm adding more and more as I go, certain functions that are just not available in Arrayfire that I think everyone might find useful. I'm adding those. Benchmarking tools. I even had some interesting conversations with people who were thinking about using these benchmarking tools to see, okay, whenever I start my application, try to decide which is the best hardware to run my algorithms on. So the program itself will decide where to run its calculation. Is it the CUDA card? If there's none available, like this laptop, then suddenly it will switch over to the iGPU of your CPU without any compilation or anything required. Another thing, allowing low-level access. Like I said, Arrayfire is there. I'm just providing a wrapper around it to make our lives a lot easier. But yeah, Arrayfire is an insanely big library. and I'm still working my way through it. So let's say you need something. You need something specific that I have yet to implement. What now? Well, you can just pull the array pointer and you can call the DLL functions yourself. There's no need to suddenly start developing your own C code to hook into some existing library. No, you can just, here's the pointer, put it in, and great. Because it's built upon Arrayfire, it will be compatible as you go forwards. And also, I'm not perfect. Let's say I made a mistake. You're not stuck. Your project is not stranded. Same for if you need a certain function. You're not stranded. You can bypass and just directly call Arrayfire if you need. And by its very nature, it will be compatible with the rest of what you've built. So let's have a closer look at G²CPU itself. So this is one of the basic examples shipped with a package. The idea is, like I said, I'm trying to make it look as much like LabVIEW as possible. Try to give it a value-based feel. So in this case, we're uploading, I see my laser is not really doing a thing here. We're uploading data to the backend. This can be the CPU, this can be an OPENCL backend, a CUDA card, anything we want it to. This code won't change. We get our references. We're doing an addition. The only thing is, in the background, there's still references. I'm still working on some better memory management. But for now, you can actually choose, OK, is it going to automatically release the memory once it's done with the operation, yes or no? And you can actually, by default, it will release it. Otherwise, you can override it. So let's say the input 2, we need it for the next calculation. So please don't release that. And then it will be fed forward, and then it will be released. I also added support for you to just directly wire in scalar values. You don't have to worry about, OK, how big does that array need to be? OK, we're back. How big does the array need to be to match, to be able to divide? No, you can just put a 2 in there, and G²CPU will take care of the rest for you. And then afterwards, when you're done, you can just pull it back out and do with it what you want. Things like data types are propagated. So if you suddenly have a U32, and then you have a complex number, but you also have floating points, the colors directly show you what you're using, but also the functions themselves evaluate what data type goes forward. So everything stays up to date, and like I said, like we're familiar with. Another interesting thing is indexers. We want to keep our operations on the GPU as much as possible. For loops, stuff like that, trying to search for something. It's not really what you want to do on the CPU when you're talking about 10 gigabytes, 20 gigabytes of data. Let the GPU do the work, and the CPU can do whatever it needs to do. So with indexers, in this example, you can just query data based on some other operation. So for example, here on the left, we're uploading some data with upload array. The data is visualized on top. So we have 2 data sets, some random data and a sawtooth signal. We just grabbed signal 0 here on the left with just a simple index function. And then we're using the top k function, which is just a function to grab max values, but a k amount. So if k is 3, we're getting 3 max values, and there are locations. We grab those locations. We already have the max values, and we can actually then feed them forward to these indexers. Currently, this might seem a bit complex, but these indexers, these queries, you can add a lot more to them. So we grab channel 1, and we say, OK, the indexes that we found on the max function give me the accompanying values on signal 1, or channel 1. Now, in this case, we only add 1 indexer, but these queries, we can make them more complex. We can say, OK, we want to search in this dimension with these indexes, and in this dimension with these other indexes, but also we have these other indexes that we also want to put in there. It can become quite complex. We can add multiple. There's not just this 1 index that we have to add. So again, we can make the GPU just do the work for us. Another interesting thing is vectorization. So this is something that people that are using Python already are quite familiar with. But for us in LabVIEW, it tends to be a novel concept. Like I said, we're used to LabVIEW being the fastest thing. So in this case, we can actually say, OK, we have mean all, which is grab the mean value of everything that's in the array. Or we can say we have 1,000 channels coming in, all in one dimension. And we just want to have the average value or the mean value for each channel. Instead of just iterating through all the channels, we can just mush them together in a 2D array to then get a 1D array out with a scalar value for each channel, which is quite interesting. So on the LabVIEW side, we don't need loops, we don't need indexing, we don't need to think about parallelization. It's just, here's the dimension that we want to calculate, have fun. This is, by the way, a simple example of an RMS calculation on an n-by-n matrix. Talking performance on this, why this is also interesting performance-wise. I ran a quick test. So just 1,000 channels with 1,000 values. If we would iterate through them, it would take about 100 milliseconds. If we use this type of vectorization where we say the GPU does the work, it dropped down to 0.85. So that's quite a drastic difference. And yeah, this was just a subset of all the functions that were available. But as you can see, there's a vast collection, which is already outdated because I'm working on the vision libraries. But we have arithmetic, Boolean logic, statistics, signal processing, linear algebra, array management, also device management, with more to come. So I did some tests. I did some brainstorming to see, are there things that I can't do with it? I'm still trying to find something that I can't implement without that I just can't implement with this library without going back to the CPU. So that's what I found with Arrayfire. Another interesting thing, like I said, we're not on an island. Let's say we want to communicate with our embedded development team. They're doing something in C, C++, maybe Rust. Yeah, we can just call their DLL or call their environment. If they're sharing memory, we can just say, here is the pointer. Go have fun. Once you're done, give me something back, or maybe not, or maybe the other way around. And because Arrayfire is already available there, it is by its definition just compatible. Now, let's say you're working with an environment that doesn't share memory with you. Not an issue. Arrayfire itself has some file functions, so we can just use those. So let's say we want to send something to MATLAB, some really big data set. We can just call the Arrayfire function to save everything to file, and then just tell MATLAB to open it. The scientists are using MATLAB. They don't have to think about, OK, how's this data structured or anything. No, because they're using Arrayfire. By its very definition, it is compatible. Now, next up, benchmarks. First, I'm going to talk about synthetic benchmarks. Sorry, words are hard. These types of benchmarks, I hate them because they don't represent reality. They're just, hey, this is how fast this specific thing on the GPU works. But if you need to go the long way around, but with a really quick library, then still it takes longer than if there's a slower library. So in this case, this is more to give you an idea of the potential performance that you could get. Don't look at the numbers, just look at comparison, in my opinion. So we have an NVIDIA RTX 2060. I see I made a typo there. I do apologize for that. Which I approached with a CUDA and an OPENCL backend. So I tried to see, OK, what does performance look like? And who would have known the NVIDIA technology is a lot quicker on the NVIDIA hardware. But still interesting to know. So instead of saying, OK, I'm going to use OPENCL every time, let's dynamically choose that. But another thing that's interesting, so this was on some kind of gaming laptop. We have the CPU, which is on white. So what Arrayfire does when we do a calculation, it is automatically using all CPU cores if there's enough data. So we don't have to think about loop iteration, parallel loops anymore and how they fit in the arrays. We can just say, please add those two together, and Arrayfire will take care of the rest. And then you see the iGPU sitting there lonely down there. But it's not irrelevant. First of all, this is a gaming laptop, so they just put the bare minimum of iGPU in there if you're watching YouTube on the train and you're not playing video games, then let's shut off that power-hungry GPU. So that's one of the reasons why that's so small. But let's say even that's the case. So your CPU in a normal application is doing a ton of data acquisition. We're doing data logging. We're sending stuff to the UI. Let's be honest, probably the operator is watching YouTube at the same time, so also grabbing some processing while they're there, maybe checking their emails, SharePoints, ton of different stuff. That iGPU is sitting there pretty much idling, so we can actually just hook in on it and say, hey, I need to do a ton of low-pass filters to visualize. There you go, and once you're done, give it back to me and I'll show it on the screen. So that's where this within designs could be potentially really interesting. This one is a desktop. The only reason I added this is to make you aware that not every CPU has an internal GPU. If you try to hard code it, you might get some issues. Now let's talk real life. So we ran a pilot at ASML where there was this system where we were verifying just a vision system, grabbing a ton of images, checking for noise, artifacts, checking if everything was scaling properly, non-linearity, that kind of stuff. And you know how scientists are, especially at ASML. They're really picky on, it needs to follow this algorithm because it's cutting edge, it's bleeding edge. So yeah, with this, we implemented the same algorithms. And going from LabVIEW, where the analysis part, it was a really big amount of data, went from 23 to 29 minutes, depending on the computer it was running on, all the way down to 97 seconds. Which, if you're in a clean room and you can't use a station for 23 minutes, it's expensive. A clean room is expensive. With this, that was just enough for them to quickly make some notes on the paper and they could continue once again. So this is the real life, or this is what we encountered in real life. It was with a, I think it was a 3070 graphics card, but of course, better hardware faster, cheaper hardware slower, but you can really fine-tune it if you want to. Next up, additions. So this was a lot of work, and there's a lot more work in the future. I'm adding a ton more functionality. So these licenses, I am making them perpetual, but there is a development license, there is a runtime license. I was hoping to have the community edition already up by this presentation, but I'm expecting it to be somewhere, I think next week or the week after, with the idea just being, if you want to do something, if you want to have fun, if you're trying to figure something out, if you're learning, just go and have fun. But if you're a company, if you're saving time, if you're, and by time, money, it's best to help with the future of the package. Hardware is expensive, software licenses are expensive. And just the sheer amount of time that I spent on this and am gonna spend on this, yeah, I can't pay everything myself, let's just put it that way. So yeah, those are the additions. Let's see where we at on time. Well, okay, so the roadmap. So like I said, I already have the basic functionality in there. Most of it just already works with vision parts. But Vision itself, for example, is not yet implemented. I'm working on that. But let's say you need it. Well, you can already call the DLL itself, go out of the G²CPU environments to then jump back in. So Arrayfire itself already has a ton of things on feature detection, image processing. So if you want to go AR, go right ahead. Once that's done, I want to finalize everything on multiple device support. So currently, it's still a little bit spotty being able to switch between devices. So I am working on that so that you can, for example, have multiple GPUs running at the same time while your CPU is also doing something and your internal GPU is also doing something. That will follow straight after machine vision, because otherwise I have to do all that work all over again after machine vision is implemented. After that, Arrayfire has also a ton of GPU rendering functions, which I will try to implement. Plots, histograms, surfaces, vector fields. Great if you want to do 3D rendering, but also great if you just want to visualize a ton of data and you don't want to lose the processing time on trying to decimate it with some kind of strategy. After that, Arrayfire has some machine learning functions, but there are also environments already available based on Arrayfire that use machine learning, so I'm still seeing what I'm going to do with that. And once that's done, I want to add real-time support. So remember, it's open source. We have access to the source, so I want to recompile it for Linux RT. So you can put it on your PXI chassis, maybe add an external GPU to it. Maybe on your C², just plug an external GPU on it and use that as a processing environment. Quick disclaimer, this can change if suddenly 100 people tell me we want real-time support yesterday. Of course, I will change the planning. So yeah, with that, I want to thank you all. I hope you found it informative. I hope you maybe got inspired to do something with high-performance computing, or maybe you got inspired for your own library on how to really get the most out of LabVIEW. So with that, thank you very much. And are there any questions?
Hello, yeah. Obviously, there are different cards and different processors. Is there a way to just look at your computer and go, right, I'll run a bit of code just to benchmark what sort of improvement in performance you can get with the G²CPU?
It's a bit hard, of course. It depends on memory bandwidth. We're talking real low-level elements. But that's the exact reason why I added the utility.
Yeah, I was going to say that hang on.
Getting there.
Yeah, the 2D, for example, could you just run a test where you just generate a massive 2D array of random data, turn it and generate, do it in LabVIEW on your CPU, and then do it on the GPU and go, well, your improvement's 500% or 5,000%.
Yeah, that's actually one of the reasons why I implemented this, to see what is worth changing over, seeing what is worth putting on which targets.
Yeah.
That's why I added this, because for us it's really important also to know from what size of arrays does it become important. If you're talking, you already saw in the graph, if we're using small arrays, it isn't that really useful to go to the GPU. So with this, you can actually, for example, fine-tune at what's the sweet spot to get your batch sizes.
Thank you. Very processor demanding processes are always related to image treatments. Does EMAC work on it, or have you something for it?
So yeah, I need to go back to the hands. So I am working on image processing, and I am working on making it in certain way compatible with iMac. So you can, for example, have the reference going into the library, and in the background it will change it so that it works with Arrayfire and also the other way around. Does that answer your question? Cheers.
Given the previous talk about avoiding the licensing hell at the end of the project, what is your plan for the licensing structure? I mean, not the number, but maybe more the technology to use.
So there are just NI licenses. So this is being distributed through the NI Tools Network. But I'm a firm believer in perpetual licenses. So when you have the runtime license, you have the runtime license. There isn't I don't want to make the landscape more crowded than it is. So I want to stick with this like it is right now. I don't have plans to go, oh, but you have Vision, so it's going to be a separate license, and you want to have this, and it's. I want to keep it simple. This is just a means for me to be able to further develop the platform. If there's a lot of demand, I might revisit pricing because I'm not expecting to pay off my house on this one. Let's put it that way. So, yeah, it's purely to justify the amount of money I'm spending myself on this to develop this further and also to help you guys. If you have an AMD GPU, okay, how does that work? What's the performance? I need to buy that. I need to develop it. I need to troubleshoot. So you all don't have to. And that's where this is coming from.
Thank you.
Yeah.
Okay, awesome. Thanks very much.